Yeah, I guess as the title says, I want to give you a very practical guide to deep learning. I know there's been one talk here before on deep learning which went through some of the theory. I'm not going to talk about backpropagation. I'm not going to talk about dropout. What I am going to talk about is a little bit about how deep learning has gone from the space of being really exciting in research to starting to move into the more commercial domain. I'm going to introduce NearMap to you and kind of what we do in our data set before leading into a practical example on our data, which I know isn't something that people do a lot, talk about Intel company stuff up here, but I'm able to share it with you today. So let's get into it. Research to industry. Well, if you're going to start somewhere, it has to be ImageNet. The ImageNet data set has 22,000 categories for images and 1.2 million images, and it was built in 2012. That data set is often slightly confused with the competition, which has a stripped down easy problem of only 1,000 different categories. And the goal is to predict which of those categories an image is best represented by. This is an example here of a Savoy cabbage, and you can see different views of it, and there's all sorts of crazy stuff in there. And it's really been considered the benchmark for computer vision performance over the last 5 years, and I believe 2017 is the last year that competition will run like that for reasons that will become apparent shortly. So where did we come from? Well, you can see this graph here. On the left, we've got something called AlexNet in 2012. That was absolutely groundbreaking in that on this problem with 1,000 classes, it was able to get the correct answer in the top 5 about 84% of the time. Now, people in computer vision who've had any interaction with it will know that that is a staggering achievement. What is even more staggering is the progress that's happened since. You can see year after year after year after year after year, the error rate just goes down and down and down until they think they're pretty much at the sensible limit of this problem and data set, which is why I think they're considering halting it there. A more useful measure for most people who think about things is the top 1 accuracy, so which the most likely prediction is, how often you get that right. So AlexNet gets right about half the time, which doesn't sound that great until you remember that by chance it's getting it right like 1 in 1,000. And we're all the way up now to pretty much 80% of the time you get the top 1 out of 1,000 correct, which is, whether you've been in computer vision or not, that's pretty mind-blowing. Along the way, obviously a bunch of toolkits emerged as different people got into it, different research groups. There's a lot more than I've got on the list. I'm just going to talk about a few of them that I think have a particular reason to be up there. You heard Jamie from Kaggle and now Google talk about TensorFlow a little bit. That's emerged as the Google project, which can do computation, kind of graph computations on CPUs and GPUs. And recently they've started talking about making these things called tensor processing units available to mere mortals to play with. And I think there's a really interesting parallel there between what happened in Bitcoin mining and what's happening in deep learning, in that they started with CPUs, then they moved to GPUs for mining Bitcoins, but now anyone who mines Bitcoins is using special custom designed computer chips in order to mine Bitcoins. And it doesn't take too much imagination to think that that's the way things are going to go with deep learning. TensorFlow is reasonably low level. Keras is, if you're familiar with the R package Caret or scikit-learn, it's kind of that level of interface into solving deep learning problems. They describe it as an API. I think the guy who runs it, it's not officially a Google project, but he's at Google, so it's kind of the same thing. Then you've got Caffe, which is a fairly venerable research framework, but that's still going and still developing. So there's a lot of frameworks still developing. It hasn't yet settled down to these are the couple that work. MXNet is one fewer people have heard of. I think, I heard Jamie mention it before. Just recently, Amazon has announced that they're going to make it their deep learning framework of choice. And they've kind of made murmurs about doing similar hardware type optimizations as what Google's doing with TPUs. So I guess the long and the short of it is that, from my perspective at least, Keras and TensorFlow makes a pretty safe bet, but it's also going to be very interesting to watch what Amazon's doing. So you really see these frameworks going from a purely kind of researchy type domain to big companies putting big money behind it. And these things, with Amazon's announcement last year and and Google talk about it now. This is really absolute cutting edge in terms of practice as opposed to possibility. So we've got frameworks. We then need to work out architectures. I showed you the slide with the different architectures over time and how they get better and better. I'll just give you a quick walk through some of the main ones. The original AlexNet is, as usual, it's not the best because it's been improved on. It's often used as a benchmark, but it's not super efficient, and obviously things have beaten it since. Inception is kind of the branding for Google's line of architectures. You might be slightly confused by seeing GoogleNet, but it's all using the Inception module, which is kind of a Google invention for making deep learning models more efficient. So rather than just shooting for performance, they're saying how can we actually run this stuff at a mind-boggling scale. Now, it's really interesting because if you thought that Google was the only player in this space, and it kind of looked like it for a bit, let's just jump back to 2015. This jump here where the error rate pretty much halved, that was Microsoft research coming in and saying, hey, we've got this thing called ResNets, which we think is pretty good. And there's now things called Inception ResNets, and it's all crazy. The last architecture I'll mention is VGGNet, which is a very nice kind of simple network which just uses 3x3 convolutions, so it's kind of nice to look at. I've heard that it's a bit fiddly to train and not super efficient, but it also gets pretty good results. So there's all sorts of architectures to choose from. Again, many different players involved. And then we come to talking about pre-trained networks, which many of you've probably heard of. Basically, building those networks that can solve, ImageNet with an 80% top one error rate, top one accuracy rate. Training can take weeks on multiple GPUs, right? This is not an easy thing to do. You've got to set up the hardware, and you've also got to have a fair bit of know-how and experience to do it. So the concept of a pre-trained network is where you can simply download the model that someone has built, all however many millions or tens of millions of weights there are, download those values, and you can use it yourself for running prediction or doing what's called transfer learning, where you adapt to a new problem. I'll show you just in this one kind of beautiful line of Keras code. This line goes and grabs the Inception v3 model trained on ImageNet from somewhere on the internet, whatever the latest version of it is, downloads it to your machine, loads it up as a Python object that is capable of running predictions via TensorFlow on whatever GPU you've got on your machine in one line of code. Now, if you're someone who wants to have a play with deep learning and has been looking at it from the outside for a few years and thinking, this seems a bit fiddly and tricky, now is really a game-changing time for new people to get in and play with it, because in one line of code you can do all that. This thing to actually do the predictions, those first two lines are just about doing a plot, the next two lines are loading the data. You've got one line for actually pre-processing the data and running the prediction, and then one we're going to decode the predictions to go from a machine-readable form to what us humans recognise as those ImageNet classes. So we've got to start with cats because, it's deep learning, and it's all about cats. So I don't know much about species of cats, but I did a bit of Googling for an Egyptian cat, which this pre-trained model says there's a 44.77% chance that this is an Egyptian cat. It looked pretty much like an Egyptian cat to me. Maybe someone can verify or deny that later. Maybe it's a tabby. I think it's impressive that the top 5 are all types of cat. I think that little guy would probably like to think he's more than, 0.3% chance of him being a snow leopard, but there we go, that's what he's given. Let's see if it was a fluke. We got this guy. I kind of did Googling here, I'm like, looks a bit like a cross between a Persian and Siamese cat. Again, I'm not a cat person. 4 of the top 5 are cats. There's bow tie in there, which I think people can kind of see where that comes from. And that it's almost the bow tie in there that makes this more believable, in a way. Because it's doing something that you or I might connect with in terms of how it's making the decision. All right, let's move on to something else. What about this guy? Well, we've got a theatre curtain, absolutely. Windsor tie. I can't quite see if it's a full or a half Windsor, but I think it's a Windsor tie. A bolo tie, I had to look it up. It's, those string ones on American Westerns? I'm thinking maybe the microphone stand, maybe? I don't know. Academic gown, you're wearing black, you're in front of a theatre curtain, pretty good odds of it being, you being an academic. What's missing? What about the guy in the middle? If I was going to pick one human being who had presence, who was highly recognisable, Arnie's a pretty top pick, and he's not even mentioned on the list. So you think, hang on, what's going on here? Well, let's have another crack. Let's put him in Terminator mode. 4 of the top 5 predictions here are types of fish. He's got this kind of metallic thing going, and you know, the kind of funny eyes, and maybe the jacket's a bit fish-like. But I was really intrigued by this, so I had to kind of go looking at the internet categories. And what I discovered was that they don't really have a people, like a person category, or anything to do with people. There's lots of pictures of people, but the class is not about what the person is. So if you look at fish, it's often like a fisherman holding up a fish. So maybe it's kind of the metallic face thing going on, but maybe that looks a bit like a fisherman's jacket. And what you get from here is that, yes, we can do magical things, but you throw something unfamiliar at the model that it hasn't seen, it hasn't been taught to recognise before, and it just falls to pieces. So that's probably something to keep in mind when you're thinking about the magic of deep learning. What else have we got? Well, let's look at where we are right now with an image from Nearmap. I'll talk a bit later about what we actually do, but that's a top-down view of this building. Coil, dome, jigsaw puzzle, maybe? What about that? That's surely more promising. You get a top-down image. Joystick? Toaster? Maybe a car looks a bit like... that's hard to kind of fathom. Whoa, what's happened there? That wasn't meant to happen. That's what happens when you use Jupyter Notebooks as your presentation platform. It is possible. It takes more effort than you'd want. So, a swimming pool is an oscilloscope, tank, maybe like a fish tank, hopefully, but that's way down the list with a 4% chance. This swimming pool, a big community swimming pool, surely recognisable, very recognisable to us. Maybe like a solar dish or like a laptop or something. And here we see not throwing an unfamiliar class at it, but an unfamiliar type of data or an unfamiliar perspective of data. That ImageNet is all these kind of front-on images of people and things and what's going on. So again, we've made the model fall to pieces by throwing something at it that it doesn't know about. So let's think about this kind of idea of off-the-shelf vision APIs, which people love to think, oh, surely the next thing is we don't need to do any deep learning ever again, we'll just use an off-the-shelf thing. Not quite the case. You can kind of think of it as their imagination in terms of what classes they've been trained on, and it's pretty easy to confuse it with an atypical presentation. When you see things getting confused and people investigating causes of error, it's because an image is, it's zoomed in a lot more on a part of the thing, which it normally wasn't in the training set. Which everyone has always known who's been in modelling, that if your training set is not representative of what it observes in the real world, it won't work as well. Exactly the same thing is true in the magical, wonderful world of deep learning. So let's now look at Nearmap. It looks like we're going to need more than that one line of code to do something useful with our data, based on what I showed you. So the question is it worth it? What's the point? I'll show you here, this is just a screen grab of our main product, which is, this is this building getting built since 2009. We fly planes over major populated centres and take high-res imagery, we stitch together into photo maps and make that available on a subscription basis to companies. So you can see that this building evolving over time, all sorts of interesting things happening, different kind of lighting and shadow conditions. As things work through, you'll see this bit kind of suddenly goes from that nice bit into flashes into dirt and then back again. The rate of change that you observe. So we've got this kind of level of data pretty much over the whole of Sydney. We cover, something like 90% of the Australian populated areas and maybe 70% of the US. And we've taken our first captures in New Zealand. So that's the data set. So I guess why machine learning at Nearmap? Partly the timing. Deep learning took off in the research world. We saw the first non-mature research. We saw the first mature research tools really come up last year. And this year we've seen that like the heavy hitters come on board saying we've got hardware, I can press a button and get a big GPU cluster spin up on EC2 and run something in a matter of seconds. It's a pretty exciting time for deep learning. Our data set, we've got that kind of 7 centimetre resolution photo map versus satellites typically like 30 centimetres up to metres. We do frequent coverage of populated areas. We take many viewpoints. So I showed you the top down. On the passes, we also do kind of 45-degree angles from different views, which a lot of customers like. And we've just released something called the HyperCamera 2 system, which is going to bring 3D point clouds and meshes shortly, as well as more viewpoints and higher resolution data. So it's a pretty cool data set. Customers, we have them, they are real, they pay us money to see our photos. We can probably do more for them. Their main thing that they want to do is to not have to go on site when they don't need to physically interact with it. So you've got engineering companies, doing assessment, you've got solar installers, you've got insurance companies, governments, all sorts of people who just want to see what's going on in an area without having to turn up, and that creates a lot of efficiency. All right, so it's time for the practical example on near-map data. What are we going to do? Well, let's have a crack at fixing up that swimming pool issue with the oscilloscopes and whatever else it was, laptops. We're just going to take two 300 by 300 metre areas, one in West Pymble and one in North Sydney. The North Sydney area has about 27 swimming pools in it, big data. We're going to use that as our training set. West Pymble uses as our prediction set. It's got 10 normal backyard pools and a big community one. We're going to use convolution neural networks with Keras and TensorFlow. And there's our training set. Looks nice, lots of little pools. That's not the kind of highest resolution, that's just to show you the extent of it. There's the test set. So kind of the tagline of this talk was obviously a bit of a cheat. 27 examples clearly isn't enough to learn on. So what can we do? Well, if we grid the world into like 4.5 metre squares, we can get about a factor of 4 increase in our amount of effective data, because each pool is represented by a bunch of squares. Then we can take all the historical surveys we've got. And in that West Pymble spot, that's kind of on the overlap point between two survey areas, we've got 70 time points on that. So that gives us a pretty good multiplier. So if we zoom in to kind of the higher res stuff, that's pretty much full resolution. That's the gridded world we're looking at. So we just turned 27 examples into 3,000. So now we're talking something possibly practical, but when people talk convnets, they're usually talking masses of data. We're talking 1.2 million images and thousands of classes. Can we do it? Well, Francois thinks we can. And he booked Keras, so I believe it. So he wrote a really nice blog post on how to do this with 1,000 examples of cats and 1,000 examples of dogs, using a nice, simple neural network from scratch, getting 80% correct performance. And then he shows a pre-trained network that's adapted that gets 94% accuracy. So it is possible to do deep learning with smaller amounts of data. So we're going to kind of follow his blog post and have a crack at that really simple baby convnet that he trains from scratch. What does it look like? Well, it's just this. Again, this is, I didn't design this, he did. There's really just kind of 3 convolutional layers, each with max pooling and ReLU activation, for those who know what that is. If you don't, then don't worry about it. There's a dense layer, and then we use dropout and a sigmoid to predict. So as far as neural networks go, that's small. So remember those ResNets have like 150 layers. So here's a little bubby network that we're going to train from scratch. So we're loading some training and validation data. You can see here we've got, the survey date, because we've got those multiple time points, we've got the grid location, whether there's a swimming pool there, whether we interpolate it as a time point. And then we've got an image patch. We're obviously taking a context patch around our 4.5 metre grid to help us make decisions. We've got a validation sample as well. Then we just set up some data and do some configuration for Keras. So it's not quite as simple as something like scikit-learn. It's got a scikit-learn interface, but it's pretty friendly. What's commonly done in the deep learning field is to do random augmentation to images. Now let's go back to why we do that. Back in the distant past, maybe, 5 years ago or so, in computer vision, people would say, I want to carefully construct a feature that is invariant to rotation, invariant to color changes, invariant to who knows what else. Whereas in deep learning land, you kind of just say, well, we're going to run through multiple passes of the data anyway. Why don't we just kind of flip it and spin it around and smush it and things and see what happens and create the invariance by doing that. So I've got my kind of cheating historical data invariance, plus we're going to do some normal invariance. Then we're going to use some Python generators, which, for those who know what they are, they're really cool. Thanks, Mark. You can load a little chunk of data into memory, compute on it, and throw it away, and then load another chunk. So you can scale to an infinite data set without running out of memory in a fairly easy way. Then we can define some callbacks. So we can basically tell Keras to start learning, and you can say, while you're learning, can you just do some things on the side? So can you just save whatever the best model is at the time, and only wipe it if there's a better model that comes along? So you've got this callback here, just kind of defines only save the best model according to the validation logs. So you just keep whatever your best model is. This one here says spit out logs to a directory, and then there's this effectively like BI for deep learning package that you can load those logs in a web app and see what's going on with your training. And finally, we're going to actually train the model. I was going to do a live demo, but I chickened out. But we could do it. This is an IPython notebook and it runs end to end. So we've given it our generators saying this is where I want you to get the training and test data from. We're telling we want to run 10 epochs, which is 10 passes through the data with randomization and a certain batch size, and here are the callbacks that you should use. Now doing this on a MacBook from a couple of years ago took 1,374 seconds per epoch. Or I can just press a button and spin up an EC2 instance with a K80. That's a big beefy GPU for those who don't know what that is, and that takes a tenth of the time. So that's what I do. So we do that, we train the model, and the obvious question is how well does it work? So we're going to compute predictions on the test set, and we're going to build confusion matrices and kind of show the output. So again, nice simple command to do predictions. We're predicting on a lot of slides at that 300 by 300 meter area, so it does take a bit of time to predict, about half an hour. Then we want to actually print out the predicted results, and we get this. We get RSC AUC of 94.5%, and our confusion matrix, for those who can see in the small data there, our true positives, false positives and false negatives are all similarly sized, which is pretty impressive given the amount of imbalance in the data set. And this is 27 swimming pools in the training set, and training a network from scratch. And I knew to expect big things from deep learning, but I was pretty impressed at what was possible. This is what I call a kind of a visual confusion matrix. I'm just grabbing a sample of some true positives, false negatives, and so on. So these are things that are swimming pools, that we recognise as swimming pools. Good job. These are false negatives. And I didn't have to do too much cherry picking for this slide to get this kind of level of variation. So we've got top left, we've got a lot of occlusion from a tree. That's understandably hard. Top right, I wouldn't want to swim in either of those pools, to be honest. And I see a surprisingly large number of them. And what's scary is the moment in time that you see they're like horrible green, lovely bright blue the next step, and then, yeah, it's the parachemicals. Bottom left is kind of even worse. It's green and kind of pond-shaped, but I'm pretty sure it's a swimming pool. And then we've got that community pool, which we actually get true positives from that quite a lot, which is interesting given we never trained it on a community-sized swimming pool, just on backyard pools. And 27 of them, that much. False positives are almost a bit funny. So top left is just when the swimming pool didn't quite trigger that central hot box of 4.5 meters. Top right, I believe, is a boat with a blue cover on it. Bottom left is this lovely aqua carport or garage. And bottom right, I reckon it's the blue car. So again, kind of similar to the bow tie experience with the cat. I'm kind of looking at this going, they're pretty good errors to be making. Like if you're going to make mistakes, I'm pretty happy with that. I was almost more happy about that than the true positives. So what's next? So this was a 3-week project when I started at UNO. And that's pretty cool because the tools were there, I guess the tech is ready, and the data set was there that I could spin this up and get it going in 3 weeks. And that was a lot of fun. what can we do? We have a few data scientists for a few years. I'm recruiting at the moment, so this is my cut to sales pitch bit. So if you're in kind of into systems and automation and you want to think about how to run this kind of stuff at scale, we're not quite at a petabyte of data, but we're getting there, and we're expanding the areas we go into and generating more data. Or if you're interested in actually building real end-to-end machine learning products for customers that make a difference, then I'd love to talk to you. There's an ad on LinkedIn. And that's just a nice kind of image of the 3D data that we're starting to be able to generate. So imagine full 3D model of all cities done quite regularly. And that's it. So if you've got any questions, I'm happy to kind of stand around and take some, but yeah, thanks.
Thank you very much, Mike. Are there any questions? I'm sure there are, yes. I want to understand what was your motivation for deep learning. Did you compare something with something much more simpler?
No. I had enough of that during my PhD. I used the simple stuff because the deep learning things were fiddly to get into. I thought I'll have a crack at deep learning and see how it does. I don't really feel the need to go back to simpler things because it was such a simple experience to do that.
I'm asking this question because I have a fear that nowadays many people fall into this trap of deep learning, and especially frameworks for deep learning.
Yep.
Because they can provide this power.
Yep.
So most of the time people just model without really understanding what they're doing, just because the system returns good results.
Yeah.
So in many cases, much simpler solutions do exist. Nearest neighbor rules, simple SVMs.
Yeah, absolutely. And I have used and do use those. I think the risk of building models that just seem to look right without testing them properly exists, whatever tool you're using. You can do it in SVM, you can stuff it up and say, hey, that looks like a good result, but it doesn't actually pan out in practice. I see machine learning as more of it's a process that's fairly invariant to what algorithm you use. So I don't think deep learning hurts us really there compared to simple approaches. Using a support vector machine on local binary patterns or something, which is a simpler computer vision technique, it's not really that much more transparent what's going on. So I don't think you lose anything extra with deep learning. I think, to be honest, the only thing you really lose is computational cost. I mean, it's pretty expensive to run, and those are the decisions that have to be made when you scale them up. Is there a simple way to get the same performance? But I mean, you look at those graphs of how, it wasn't so long ago that telling the difference between dogs and cats was a dream, and now I think they're arguably better than human accuracy on species of dogs and species of cats. So it's hard to say no to that power. I guess you just got to use it wisely. A question over here?
Mike, when you showed the training data gridded at a fairly high resolution, there were a lot of pictures of only a fraction of a swimming pool. Does that have much of a bearing on how well the algorithm learns? Is it best to experiment with grid sizes?
Oh yeah, I mean there's lots more experimentation I could have done. As I said, this was a short project. So I really just wanted to see, on the one hand, the readiness of the current set of deep learning frameworks and toolkit. And on the other hand, I wanted to poke around with the new data set that I got to play with and see how powerful it was. And I got big thumbs up from both regards. Yeah. And over here.
Can you actually teach it to ignore those errors so you can improve the accuracy?
Yes, I mean, it's almost a silly example to say we're going to train on 27 swimming pools, and that's going to be our model. Absolutely, but that's when we need more data because you're starting to corner cases and we're getting the idea. If you look at the types of mistakes that it makes, and I did, I guess to your point, I did much more looking through the types of mistakes it was making. So blue tarps, for example, get triggered as swimming pools. So we're kind of, this is at the stage of recognising that kind of a bluish blob thing is a swimming pool, and that's probably where it's at. And there's fortunately not too many bluish blobs around. It's deliberately a fairly easy problem as far as visual distinction goes.
Another question here in the corner. Do you think there's any sort of compliance or legal restrictions that might come into play with this sort of data?
Yeah, I mean, with any data set, absolutely there's, to me the more important consideration is usually compliance and legal are behind, you know, what's important for real people. So it's always good to remember that real people are behind the data sets. So yes, absolutely there are considerations. But having just started there, I haven't worked through them all yet, but certainly that sort of thing is front and centre of my mind.
Here.
Yes.
How do you settle on hyperparameter tuning and even deciding the right architecture for your networks?
So I was lazy and I just copied Francois. If there's ever a case of kind of standing on the shoulders of giants, this is it, because I'm using a data set someone else built, using a content architecture that someone else built and a training approach, and just kind of added a couple of little tweaks and get great results. So I didn't do an enormous amount of hyperparameter optimization.
In general?
In general, yeah, I mean, you can do cross-validation if you can afford the computational cost. You can do a training validation test set, and there will be lots of models that you test against each other on the validation set, and then see how it goes with a separate test set. But again, with this amount of data, you can't really afford to have that number of different test sets.
I've got two questions. So first, what's the cost of running this model on Amazon? And second, if you want to further improve this model, do you think there's a long way to go, and what kind of things you should do to improve the accuracy?
Yeah, so what's the cost? So I guess Amazon, the P2 instances, you can get 1 K80 for, it's about $1 an hour. You can get one with 8 K80s for like $14 US an hour, and 16 K80s for 32 an hour. So it's expensive, but it's there because to do this. Well, you saw the prediction. So the prediction on the validation set took about half an hour. The training, actually, the training on this training set, because I subsetted it down to just balanced data, I wasn't training on the full amount. That only takes, actually I showed it, didn't I? It was like 141 seconds to train the model. I think it sounds like not much, but I'm pretty sure that's right. Yeah, because I only trained on the positive example of tools and an equal sample of negative examples rather than the full data set. So it's a pretty small set. But yeah, cost at scale is obviously a consideration that I'm going to start to think about. I like to think about scale, but yeah. Well, more data is an obvious place to go because that's not my stable data. I spent like a day or two labeling data.
From the sort of folk theorem of there's no free lunch,
Yep.
when you improve something in some way, you pay for it in another way.
Yep. Do
you think now that you're getting better at doing pools, you've got worse at doing cats?
Yeah, well, so I didn't take Francois' pre-trained network. This was trained from scratch. And again, one of the really nice things about Keras is that one of the fiddly areas of deep learning historically has been initializing weights and things, but I'm very careful about picking good defaults. So it was never any good at detecting cats, this model. But yes, if you're looking at a large network and you're tuning the network to perform a specific task, it's obviously going to start forgetting about other things. Yeah.
Are there any more questions? Okay, I will run.
So from the true positive data, that would be a training data too. If that is a training data, then what is the annotation of a training data? True only or something else?
So that wasn't training data, that was validation data.
No. If that is the training data for your system
Yeah.
and the model, what is the annotation of the image? Can you repeat the question?
So asking about the annotation of the data.
Yeah, annotation of the image, true or something else?
Yeah, I won't go too much into the detail. I can't tell you everything I've done because come and work with me and find out. But essentially, we're looking at kind of a hot box in the middle to see is there a pool there, and then context around it.
Okay, so you got some sort of the other features to crop the middle of the image, and then it says it is pool.
Yeah. So this is the size that I'm predicting on. That's That's for,
So, and then you crop the.
That's the amount of context it gets.
Do something like select some kind of rectangle box and then, okay, this are, no?
no.
Just
It's
the
just a half
depth
box.
of pool.
Yeah, it's really simple. Like
Yeah, that's cool.
I was pretty blown away when I saw the results.
I mean, in
'cause-
terms of image training data, actually, there's also actually combined associated with the tag annotation, something like the pool or cat or Persian cat, something like that, and then they understand the future of the training image data. So that's why I'm asking you. That is a pool. Just the annotation is pool or pool with trees or something like that.
Yeah, no, I just pull, not pull.
Okay, thank you.
Okay, if there are no more questions for Mike, please join me again in thanking him for a